Today we can discuss about a normal form for context-free grammars, namely Chomsky normal form. First we can see what structure needs to be satisfied by the productions of a context-free grammar to be in the Chomsky normal form. This is the structure. A context-free grammar G is said to be in Chomsky normal form if each production in the set of production is of the form capital A goes to capital BC or capital A goes to small a, where capital A, B, C are variables and small a is a terminal symbol. So, a context-free grammar is said to be in the Chomsky normal form if the RHS of every production is a string of two variables or non-terminals or a single terminal. So, these are the only two forms allowed in the Chomsky normal form. And recall that by definition, the RHS of a production in a context-free grammar can be any string of terminals and non-terminals. Non-terminals are also called variables. So, I am using these two terms, variables and non-terminals, interchangeably. So, it looks like we are restricting now the RHS to be two variables or a single terminal. Is it really a restriction? In fact, it is not, and that is why it is called a normal form, in the sense that every context-free grammar G is either already in the Chomsky normal form or it can be converted into a grammar G prime which is in the Chomsky normal form, such that the language generated by that grammar in the Chomsky normal form is same as the language of the given grammar except for the null string. See, these are the only two kinds of productions permissible in a Chomsky normal form. So, you cannot derive null string using a grammar in Chomsky normal form. That is the only restriction. Otherwise, you can get an equivalent grammar in Chomsky normal form. The only thing that you are supposed to remember is these two forms of RHS. Very easy to remember, either two variables or a single terminal. Now, is this grammar with three productions in Chomsky normal form? Recall that these are the only two forms. The RHS is either two variables or a terminal symbol. You can say that it is no, because the first and third productions violate the property. Here two variables, but in this case a variable and two terminal symbols, and here the left and right parentheses are terminal symbols. Here the RHS is epsilon, that is also not allowed. Now, if you look at this grammar with 6 productions, you can easily verify that that grammar is in Chomsky normal form, because from production number 1 to 4 every RHS is 2 variables, and 5 and 6 it is a single terminal symbol. So it is in CNF, and it is not very difficult to check that language of this grammar is same as the language of this grammar except for the null string. And in this lecture we are going to discuss how you can automatically obtain this grammar or a grammar very similar to this, which is in Chomsky normal form, from a given grammar like this. Before we see a procedure for transforming a grammar into Chomsky normal form, let us see why we need Chomsky normal form. The first application is it provides a way to solve the membership problem for context-free languages or context-free grammars. What is the membership problem? Membership problem is a very common problem in formal language theory. And here the problem is, given a context-free grammar G and a terminal string X, it is a problem of checking whether the terminal string X is in the language of the grammar. That is, whether you can derive the terminal string X from the start symbol of the grammar. That is called the membership problem. And see that in general the RHS of a production in a context-free grammar can be any string of variables and terminals, and therefore by definition infinitely many derivations are possible for a given string because the RHS is unrestricted. But the moment you restrict it as a CNF grammar, the only restriction is epsilon is not possible to be generated. You know that the RHS, the maximum length is 2, and by applying a property of that you can prove that given a string X, to check whether X can be derived you have to only consider finitely many derivations, or the number of derivations can be bounded by twice the length of the given string. So this is an application for Chomsky normal form, which allows us to get a membership algorithm for context-free grammars. Another application, which is a generic one, it enables to get easier proofs about context-free grammars. This is a particular case where we are getting an easier algorithm for membership problem. Similarly, proofs of various other results about context-free grammars become easy when you assume that the grammar is in Chomsky normal form. Later we can see concrete examples. With this motivation, now proceed and look at a procedure to convert a context-free grammar into a CNF. And before we formally write the algorithm, let us try to understand the different steps required in that algorithm by using a simple but illustrative example. Here is a context-free grammar given with 4 productions. These are the variables capital ABC, and terminal symbols are left and right parentheses. Is this grammar in Chomsky normal form? It is not, because the first, third and fourth productions violate the property. Here you have a string of 3 symbols, two of them are terminals and one is a variable, which is not allowed. This is okay, two variables. This is again not okay because in the RHS you can have a terminal but you cannot have a variable alone. So this is also violation. Similarly here, epsilon is not allowed as the RHS. So only one production is satisfying the requirement. Now this kind of a production is what is called a unit production. Unit production means the LHS is a variable and RHS is also a variable. So in the derivation, the effect is to just replace one variable with another variable, and this kind of productions are called unit productions, which is not allowed in a context free grammar in Chomsky normal form. Now the question is, how can you remove or replace this with something else? And to answer that question, let us ask this question: what we can do with the last two productions in a derivation? You can see that we can derive the null string from the start symbol. How? You first apply production number 3, where you will replace capital S with capital A, then apply production number 4, you can replace capital A with epsilon, and thus you are deriving epsilon. And if you carefully observe, so what we are doing here is we are substituting the value of A from the production 4. What is the value of A from production 4? It is epsilon. So you are substituting epsilon here, and you can utilize that fact. This can be managed by replacing the RHS A of production 3 with the value of A from production 4. So what is production 4? Is this value is epsilon. So what I am telling is, you can replace this capital A with the value of the capital A from the other production. So you are getting S goes to epsilon. So this is what I am telling. You can replace this with S goes to epsilon. It is true that it is introducing another problem where epsilon you are getting. That we will see in the next slide, how can you manage the epsilon productions. But here the purpose is to just get rid of the unit productions that we did. What we did, can we generalize? And now you see that production number 4 is not required anymore, because see, it is defining capital A and there is no way to reach into capital A from the start symbol. You can easily verify. So without affecting the language represented, you can just throw away that production. And now you can see that this step can be generalized. What we did, if there is a unit production, then you replace the RHS, which is a single variable, with its value or definition from other productions. So what is the value or definition? The RHS of a production where this is the LHS. So this is how you can write it in a general way. Suppose there is a unit production like this, then you replace this B with the definition of B from another production. So you will get A goes to alpha, right? Now even if this is a variable, you can continue this until you get rid of all the unit productions. And this is what is called elimination of unit production. This is a very simple step. What you do is, if there is a unit production like A goes to B, then you substitute the value of B from the productions where B is the LHS. And the only thing that you have to remember is that there may be multiple transitions rules defined for B. Then you have to substitute from each of those productions and you will be getting a number of resulting rules. For example, Suppose you have B goes to alpha, one production, and B goes to gamma, and B goes to beta, two other productions. Then you will be getting A goes to alpha, A goes to beta, and A goes to gamma. So that is the generalized case. I hope you are with me. And now let me proceed. This is what we arrived at. Now the unit productions are removed. Now if you look at this grammar, this is a problem. Of course the first one is a problem that we shall see later. This is again a problem. What is the problem? The RHS just epsilon is not allowed in Chomsky normal form. So how to manage this? For that you have to ask this question: how does this production help in deriving a sentence or a terminal string? How does it help? How does this epsilon transition helps? You can substitute the value epsilon for S in all the other productions. Okay, in a derivation process, it helps to substitute epsilon for S. For example, if you substitute epsilon for S here, you will get left parenthesis followed by right parenthesis, which will be a terminal string that you can derive. So how will you manage this? This can be managed by adding new productions which are obtained by substituting the value epsilon for S in the RHS of all other productions. So what I am telling is, you can throw away this production, and what you can do is, you substitute the value of S as epsilon in all the productions where RHS contains S as a symbol. We can try what will happen if we do that. If you do that substitution on the first production, you will replace capital S with epsilon. So the resulting production will be capital S goes to left and right parenthesis. So this S is replaced with epsilon. And here there are two occurrences of S. If you replace the first capital S with epsilon, you will get S goes to S. And even if you replace the second, you are getting the same production. So you are getting two more productions. When you substitute the value of S as epsilon, here you will get this production as the result by retaining this also, and here you will get S goes to S as a production. Not that here we are introducing unit productions that we have to eliminate using the previous technique. But here we are considering only how to eliminate epsilon productions, that is where the RHS is epsilon. Of course, this may introduce unit production as this. Then you have to apply the rule for eliminating unit productions. And now you see that in this particular case, S goes to S can be dropped. You can just throw away, because replacing S with S in a derivation is not making any effect. So you can just drop it. And these are the three productions that we have. Okay. Now this step also can be generalized. What we said is, if there is an epsilon production for S, then in all other productions, what you do? You substitute in the RHS epsilon for S and you will get a new production. Add all such productions into the grammar. So this is what we can say in general. For all productions of the form, capital A goes to a string where B is a variable. Alpha and beta are some strings, we are not caring about it, but B is a variable and there is an epsilon production for B. So what you can do then? You add a production which you can obtain by replacing this capital B with its value epsilon. So what you will get? A goes to alpha beta. That is what I am saying here. And you have to do that for all productions where in the RHS B is occurring. Okay, you keep on doing it. Then what will happen? After that, you don't have to retain this epsilon production, you can just throw away this and you can prove that what we are doing is correct, because if epsilon production is there, you can replace first A with this string and after that you will replace capital B with epsilon. So the same effect you are getting with a single production A can be replaced with alpha beta. And so if you do this, there is no need to retain this production and hence you can remove it. And this is what is called elimination of epsilon production. So we have seen two steps. First is elimination of unit production, which may add epsilon productions, and here you are having a rule or a technique to eliminate epsilon production which may add unit production as shown here. So you have to repeatedly do these two steps until you get into a grammar where there is no unit production and no epsilon productions. Now this is the grammar that we have, and if you look at this, the middle is okay, just two variables. The first and the last one violate the property. Now how can you manage these two productions? So I am giving you the solution first and then I can try to explain. What can I do is, I can do this. This is actually the production where in the RHS there are three simples. So what I am doing is, I am replacing the terminals with a variable. The left bracket is a terminal. For that I am substituting a variable L and I am defining L as left parenthesis using a permissible production in the Chomsky normal form. So what will happen? This L will get replaced with this left parenthesis, so this is okay. And similarly I am replacing the other terminal simple with a variable and I am saying that this variable is nothing but that simple. I hope you are getting me. And for the third one, now I can just say L and R, because if you apply this production you are exactly getting this. And this can also be generalized. What we are telling is this: ensure that the RHS of every production, if that RHS is having length more than 1, you ensure that in the RHS every simple is a variable. That is what I am telling, and that is what we did here. If it is not a variable, what you do? You replace that terminal simple with a variable and you say that the variable is nothing but that terminal simple. So we can write it like this. Suppose you have a production where there is a single terminal small a and a string of variables in the left side and a string of variables in the right side. Here notation alpha says that is a string of variables. So here the only problem is this small a. So what you do? This is what we said. Replace this small a with a variable, say capital A, and you say that capital A is nothing but small a, which is a permissible rule in Chomsky normal form. Maybe we can look at another example to get it more clearly. Consider this production. In the RHS we need all variables, but there is a single violation. According to our convention, small letters are terminal, so this must be a terminal. So what you can do? You replace that small e with a variable, let us say capital E, and you say that capital E is nothing but the terminal small e. So this is what we said. So this was not of this form where RHS is a set of variables, but this is okay. And by these two productions we are exactly representing this. Okay, so first you get in the RHS, if the length is more than 1, you make sure that all are variables. Okay, and after that you will get into this kind of a grammar, right? And here if you look at all these productions, what we did here is we replaced this with the L, S, capital R, and for L and R, you added these productions. That is what we are getting here. And here you can verify that except the production number 1, every other production satisfies the rule for context free grammar in CNF. The only problem is here. How can you manage? This is a very easy process. What you can say is you need maximum 2 variables. So what you can do is you can say that it is capital L followed by another variable x. Okay, this is okay. And then what can be x? X is representing SR. Okay. And suppose there was one more variable t, SRT. Then what you can do? Now you can say that x is nothing but S followed by y. Then y is RT. This technique can be repeated until you break all the RHS into 2 variables. When you work with an example, things will become more clear, and these steps can also be generalized like this. Suppose you have a production like this. In the RHS, it is a string of variables such that first variable is capital B, and then you have a string of variables whose length is greater than 1. That means here the total length is 1 plus a number greater than 1. So more than 2. Now what you can do? You can say that it is nothing but capital B followed by x, and x is nothing but beta. So now the RHS length is reduced by 1. If it is n, what was the length of beta? If the total is n, then for beta it is n minus 1 and plus 1 is n. So now this becomes n minus 1, and you can apply that trick again. You will get y goes to first letter of first variable of beta followed by the other string, and you can continue until you get all the productions with 2 variables in the RHS. So this again is a generalizable procedure, and if you recall, this was the given grammar, and after applying the 3 major steps that we discussed, you can get rid of or replace all these 3 violating rules with the correspondingly obtained productions. So this is what we got in our running example, and now we can try to formally write that procedure. Okay, I am just formally writing it, whatever we did. I will be copying that sentences and writing it. And first is remove unit productions and epsilon productions. We have seen rules. And after that, what you do? You make sure that in the RHS, if the length is greater than 1, all are variables. And to make that, we have this step. I am just copying it, no need to read. Exactly the previous sentence is copied. So you got all the RHS variables along, then after that you break it into various productions where RHS contains only 2 variables. This is just the previous rule that we formulated. I just copied it here, no need to read. So this is the basic procedure, and now we may look at the first step in detail, how to remove unit and epsilon productions. And recall that when you remove unit productions, you may introduce epsilon production and vice versa. So you have to do it repeatedly. Repeatedly you do that, and what you do is this is getting rid of the epsilon production. If you have an epsilon production like this, what you do is, sorry, there is a typing mistake, this should be B, not beta. This should be capital B, not beta. And suppose you have an epsilon production for B, what you do is you will be adding A goes to alpha beta, and that you have to do for every production where the B is appearing, capital B is appearing in the RHS. So you do that. Then what you do? So you might have introduced unit production. So next step is replacing unit production. This is exactly what we saw. This is a unit production. So what we do is replace B with its value. So you will get A goes to gamma. I hope you remember, otherwise please go back and see what we did. And you have to repeatedly do this until you remove all epsilon and unit productions. Not that when you do this, you will be introducing unit productions which you will remove by the second step. But when you do the second step, you will be introducing epsilon production, and that is why you are doing it in a loop until you finish. And you can prove that this is a terminating procedure. You will not end up in an infinite loop. Okay, so here we are only adding productions. After that you can just so this is the grammar that you obtain by adding all these kinds of productions, and after that you can just drop all the epsilon and unit production. They are not required because the corresponding productions are added by the step 1. So you can just throw away all the epsilon and unit productions after the steps, after the step 1. So what you are getting is a grammar without unit and epsilon productions. And then what you can do, that trick where you make all the RHS variables alone, then you break it into various productions where each production is having only 2 variables. That is what we discussed. And with this I am coming to the last slide where I am giving you an exercise problem for you to practice and understand how can you systematically transform a given context-free grammar into Chomsky normal form. Today we have seen an algorithm for converting a context-free grammar into Chomsky normal form. Thank you.